All right, in this video, we're going to go through the review questions at the end of Chapter 6, which was on the statistics of measurement error. Okay, true or false? And explain. An experienced scientist who is using the best equipment available only needs to measure things once, provided he doesn't make a mistake. After all, if he measures the same thing twice, he'll get the same result both times. Well, this is definitely false. An experienced scientist using the best equipment available is suggesting that, so this is the state-of-the-art equipment, the best of the best, the most expensive of the most expensive, and the scientist knows exactly how to use that piece of equipment. All that's going to mean is that the equipment is very precise. But in general, there never has been, and there never will be, any measurement equipment, any instrumentation that is perfectly precise. To measure the exact weight of something, we would have to see at every atom, every proton, every electron, every quark, etc. So, no, even as technology advances and the instruments get more precise, it doesn't matter. Any measurement's going to come with a degree of uncertainty. Yes, maybe in 500 years, the precision levels will have increased to such a point where what we were measuring today, the precision levels that we're measuring today, we wouldn't need to measure more than once. But still, in 500 years, it will just be zoomed into a higher level of precision, which means that when you measure at that precision level, when you measure the same thing twice, you're going to get different results. A carpenter is using a tape measure to get the length of a board. What are some possible sources of bias? Okay, so bias was, you've got the exact measurement value, which is like what God would measure, okay? And then you have the measurement you have the exact length of the board, exact length, okay? But then you've got the measured length, what you actually measured. How can the measured length be different from the exact length? Well, that's random error, like chance error, and there's bias, okay? Bias is like a systematic error. Maybe the metal piece at the end of the tape measure is bent, and so the carpenter is unknowingly adding a 1/16 of an inch to every single measurement he makes, right? That's bias. It's every single measurement is away from the exact length by that much, okay? Which is more subject to bias, a steel tape or a cloth tape? Yeah, I guess a cloth tape. A cloth tape could twist, could fray. Maybe the cloth tape is frayed, and so you have an extra 1/16 of an inch on every measurement. You don't realize it, but it's systematic. It's systematic, as opposed to a chance error. Random error is just the result of it's the uncertainty level of the measuring tape. It's based on the tick marks, right? If you have a brand new tape measure, well then even though it's brand new, you can still only, when you try and measure between tick marks, you have to just kind of guess. You give an estimate. Oh, it's about a quarter of the way between the tick marks. It's about halfway between the tick marks. So there's like random error in there as far as the exact measurement. Okay, would the bias in a cloth tape change over time? Yeah. You would think any measuring instrument, as it gets older, as it wears down, as it gets used, it starts to bias, right? You have a brand new instrument. It's giving you certain measurements, and when it's brand new, it's kind of hovering around the exact value, but then over time, things wear down, that starts to shift. Here's the exact value, and your brand new instrument is giving you measurements all around that exact value, but as the machine wears down, as the instrument wears down, systematic errors come in, and that starts to shift a little bit. And even the random errors start to spread out a little bit, and everything kind of shifts away from the exact value. True or false, and explain. Bias is a kind of chance error. False. Bias is not chance, it's systematic. If the metal piece at the end of a tape measure is bent, then that error is in every single measurement, not by chance. Okay? Chance error is a kind of bias. That's false. Chance error is the natural result of our ability to not be able to measure, to build instruments that can measure things exactly. If you have an extreme precision scale, Well, it's just there's going to be variations in the electrical currents we can't measure. There's going to be, the mechanical pieces, the springs are going to bend a little bit, and so you take all that together, and it's just you can never get an exact, perfect measurement down to the atom, to the quark, to the boson. Measurements are usually affected by both bias and chance error. True. Even a brand new tape measure, the inherent design of the instrument itself could have kind of a natural bias in it. Now maybe it would be hard to notice that bias, right, if it's brand new, but it could. Just the way it's designed, they tighten the screws just a little bit more than they should be tightening the screws into the tape measure, and so in reality, the variation is off center of the exact value a little bit. That would be bias. Okay, you send a yardstick to a local laboratory for calibration, asking that the procedure be repeated 3 times. They report the following values. All right, so the idea of calibration, you send a yardstick for calibration, is they're really trying to, for something simple like that, just a yardstick, but it's the same idea with any kind of calibration. They're just trying to tell you what the exact length of the yardstick is. And you might say, well, what do you mean? 1 yard is 36 inches. Yeah, that's true, but okay, is it 35.96, 36.01, 36.03? And I don't know why you need this level of precision with a yardstick, but that's the idea. They're just trying to illustrate calibration. Okay, if you send the yardstick back for a 4th calibration, you would expect to get 36 inches, give or take, 0.01 inches or so, 0.03 inches or so, 0.06 inches or so. Okay, so what is the question here? Maybe they meant to state this as would you expect? Would you expect to get within 36 inches, 0.01 inches, 0.03 inches, or 0.06 inches? Okay, well, the way we talked about this was that the laboratory, their general procedure is going to be that they would measure the yardstick with their measuring instrument. Well, they would do it just once, and they would already know what the uncertainty is, and they would report the uncertainty with it. That would be the idea. But let's say they didn't know the uncertainty yet. Then the idea is like they would measure the yardstick 100 times, 1,000 times, whatever. I mean, they're probably a real procedure. They would, again, when they get the uncertainty, they probably do thousands of measurements to get the uncertainty. But just to think about this as theoretically, they would measure this 100 times and get 35.96, 36.03, whatever, et cetera, et cetera. Then the way you look at, once you do it a bunch of times, you look at the uncertainty of the measurement from the perspective of the standard deviation. So they have this standard deviation, then someone sends in a yardstick, like we send the yardstick to them to get measured, they measure it, and they say plus or minus this standard deviation. We can't tell you exactly what within that amount. So just this here, we would look at if this is all of the information we had, which is not that much information, just 3 measurements, but if this was it, we would look at the standard deviation of these 3 numbers. So let's see. You've got 35.96 plus 36.01 plus 36.03. Okay, there's the average. So now let's do the root mean square of the deviation. So 0.04 squared plus 0.01 squared plus 0.03 squared, okay, divided by 3. So there's the standard deviation. So if we sent the yardstick back for a 4th calibration, we would expect to get something around 0.03 inches from 36. All right, 19 students in a beginning statistics course were asked to measure the thickness of a tabletop using a vernier gauge reading to 1/1000th of an inch. Each person made 2 measurements shown at the top of the next page. The units are inches. For instance, the first person got 1.317 and 1.320 for the 2 measurements. All right, did the students work independently of one another? All right, let's go look at these measurements. Okay, well, first of all, I'm noticing person 2 and person 10. And to me, this is a good example of an outlier that I want to remove from the data set. Some outliers you might decide not to remove. And again, what exactly is an outlier? How do you classify it as an outlier? We'll talk about that later in the course. But to me, this is obvious. Something went wrong here with these measurements. So let me put this data into Excel. Okay, so there's the data, and I put the outliers at the bottom of the list. What we can do is, let's start by getting the average of the two measurements for each student. Okay, and what the first thing I noticed is that these two students, not only were they enormous outliers, but they got the exact same measurement. So for both measurements. So to me, these two didn't do theirs independently. Okay, but if you look at all the other 17 students, actually, it doesn't look like anyone got the same measurement when you average out the two measurements. So these were all working independently. Okay, but let's go ahead and, just to get a sense for this, let's see how many standard deviations these measurements are away from the average. So we use, so we got all of these measurements. There's a standard deviation. So, okay, if we take this, all right, so this divided by this, about 3.6 standard deviations. So I thought it would be a little bit higher. That's still a lot. And that shows you there was an example in the textbook where there was a data point that was 5 standard deviations away from the average. That's like that's what they said was like a minor miracle, like winning the lottery. This is just 3.6. I mean, look, if you're measuring the thickness of a table, and the thickness must be somewhere in this 1.3 something range. There's no way you could get 13.25. Something went wrong. That can't. This is not. You don't want to consider this as part of the data set. Okay, but it says, some friends of yours do not believe in chance error. How could you use these data to convince them? All right. Well, okay, let's get rid of these. I think our friends would agree that these guys were playing around or something went wrong with the device. Well, okay, we just need to show them that there's a standard deviation here. We have all of these measurements. Okay. And they all weren't just centered at the same point. These all weren't the same measurement. Everyone was giving it their best effort to get as close of a measurement of the thickness of the table as possible. And here's a standard deviation of this data. I mean, you could plot this on a histogram, right? And show that this data, it has like a spread to it. That's the chance error. Okay. In one course, a histogram for the scores on the final looked like the sketch below. True or false? Because this isn't like the normal curve, there must have been something wrong with the test. Explain. So, no, false. False. Because when you think about a normal curve, something that you expect to be normally distributed, that just means it's going to be like a pure random process with there's no like kind of systematic confounding variables involved. It's just a pure coin flip. Not even by a human, because a human could, even psychologically want to get heads or something. I mean, there's just no confounding systematic variables. Well, with a test, an exam, I mean, you could have some students, how much, it might be a certain class where there's more smart students than not smart. I mean, you wouldn't even have to expect this to be symmetric. This is symmetric. It doesn't even have to be symmetric, much less normally distributed. Now, maybe the type of distribution could explain something about the test, how the test was designed, but something wrong with the test? No. If there was a skew to low grades, the test was too hard. Skewed towards the right, the test was too easy. Here it's symmetric, so maybe the test wasn't too hard or too easy, but I don't know. But as far as something wrong with the test, no. Just because it's not normally distributed, no. Okay, fill in the blanks using the options below and give examples to show that you picked the right answers. The standard deviation of a list is 0. This means what? Okay, well, we know that the standard deviation, if we have a list of values, you've got the distance of each value from the mean, and you take the root mean square of that list, and that's the standard deviation. So if the standard deviation is 0, then if we think about how with the root mean square, it's not like with an average, you can have an average of 0, which means that some of the values in the list were positive and negative. But if a standard deviation is going to be 0, for a root mean square to be 0, then all of these deviations have to be 0, all of them. Even if you had, even if one of them was negative, another one was positive, when you square it, it's still going to result in a positive root mean square value. So in that case, this means that all the numbers on the list are the same. Okay, the RMS size of a list is 0. This means what? Okay, yeah, this is kind of confusing. What they're saying here is the standard deviation is the RMS of the deviations list. They're saying that the list itself, the RMS is 0. Well, that means that all the numbers in the list are 0. You can't get, it's not like an average where you could have some positive numbers, some negative numbers, and it averages out to 0. RMS doesn't work that way. You're squaring every number. You're taking the sum of the squares of the numbers. So if you have any number in a list that's non-zero, RMS can't be 0 then. Okay, a personality test is administered to a large group of subjects. 5 scores are shown below in original units and in standard units. Fill in the blanks. All right, so here's the original units, here's the standard units. And so, okay, let's look at the 79 and the 1.8. We've got, so 79 minus the mean over the standard deviation is equal to 1.8. That's 18 divided by 10, so 9/5. Okay? Because we know this is going to be 79 is greater than the mean. The distance of 79 from the mean divided by the standard deviation is equal to 1.8. All right, now we can do the same thing with this second data point. So 64 minus the mean divided by the standard deviation is equal to 0.8. That's 8/10, so 4/5. Okay, now what we can do next is let's take the reciprocal of both of these equations. So, okay, so 5/9. Okay. All right, 5/4. Okay, so now if we cross multiply, then what we can see is that we'll get, and set the sigmas equal to each other, 5/4 times 64 minus xm is equal to 5/9 times 79 minus xm. Okay, and we can plug this in, so 5/4 times 64 minus x is equal to 5/9 times 79 minus x. Okay, that's an equation, and we'll do algebra solve equation 52. So the mean is equal to 52. So xm is equal to 52. Now sigma is equal to, you have 5/4 and then 64 minus 52. So it's 12. So 4 times 3. Sigma, the standard deviation is 15. Okay, so, all right. So now if the mean is 52, then the standard units here are going to be, this is 0, right? This is it's not any distance from the mean. Okay, let's see. Here we've got, 72 minus 52 divided by 15. So 72 minus 52 divided by 15 is 4/3. 4/3 is, so one, I'll just put 4/3. Okay, now what we need to do here for this last data point is, what we can do is, so we could use the standard units here. I mean, I guess we could, let's do both just to check. So if we do 79 plus 64 plus 52 plus 72, so 267 plus this last data point, 267 plus this last data point, divided by 5 is equal to the average. So 52 times 5 is 260. You have 267 plus x is equal to 260. So minus 267 minus 7. So this should be minus 7. Is that right? Let's see. So it seems kind of low. So, okay. 52 seems really low. Minus 7. 59 divided by 15. Well, that can't be right. So maybe they're wanting us to do, they just gave us, they did this personality test to a large group of subjects, so more than 5 subjects then, and they're just giving us 5 sample scores. So you can't look at, these are 5 of the maybe 100 subjects or 1,000 subjects. So we can't do, I can't do it that way to get that, to use the average in that sense. I've got to do this. So it's going to be the mean minus this score, x. Or no, it would be, is that right? Yeah, that's right. This is going to be something like 30 or something. So you get a 52 minus a number that's less than 52 is going to be a negative number divided by 15, and that's going to be equal to minus 1.4. So minus 7/5. Okay, so 52 minus x is equal to 15 divided by 5 is 3. 3 times minus 7 is minus 21. So minus x is equal to minus 21 minus 52 is minus 73. So x is equal to 73. Oh, wait, hold on. No, that's not right. No. Okay, hold on. X is going to be less than the mean. So it's going to be like this. X minus 52 is going to create the negative number. So 15 times, you have x minus 52. 15 times minus 7/5, that's minus 21. Minus 21 plus 52 is 31. There we go. So this is 31. Okay. Among first-year students at a certain university, scores on the verbal SAT follow the normal curve. The average score is around 550, and the standard deviation is about 100. What percentage of these students have scores in the range 400 to 700? Okay, so let's get here's the normal curve formula. And so I'll put this into the calculator. So, okay, square root of 2 pi, okay, times e to the minus x squared. Okay, store this. There we go. All right, so average is around 550, standard deviation around 100. So what are the standard units here? The z-scores here. You've got 400 minus 550. 400 minus 550 divided by 100. Okay, now 700 minus 550 divided by 100. So, okay, there's the two z-scores. Now we just need to integrate from minus 3/2 to 3/2 equation E with respect to X. 34.2%. Okay, there were about 1,000 students with scores in the range 450 to 650 on the verbal SAT. So about how many of them had scores in the range 500 to 600? Fill in the blank, explain briefly. Okay, so in the range 450 to 650. So let's get those z-scores. We'll probably need to use those. So 450 minus 550 divided by 100. 650 minus 550 divided by 100. Okay, so we could go ahead and get the, I'm sure we'll need this. So what's the percentage of that? We'll do minus 1 to 1. So 29.8%. Okay, well that's the 1,000. Okay, we still might need that though. So this is 29.8% of all of the students that took the test had scores in this range. So we can get the total amount that took the test by doing 1,000 divided by this divided by 100. So that's how many took the test. We might need that. But as far as 550 to 600, or 500 to 600, so we've got, let's see, 500 minus 550 divided by 100, and then 600 minus 550 divided by 100. So, okay, let's put this in, minus 1/2, 1/2. So that's 18% of the total. So this divided by 100 times this, about 618 students. Yeah, so we just use we're assuming that this is, they told us that these data points for the score, the verbal SAT scores for these certain amount of students followed a normal curve, normal distribution. So we can use the normal curve to get percentages of students in different intervals, right? And so they told us that 1,000 students scored in this range here, and this was the first time they gave us some information regarding an actual number of students. And so we could use this to approximate the total number of students that took the test, because we knew that we could use the normal curve to get a percentage of students that scored in this range, apply that percentage here to get the total number of students. Then with that, we could have actually come here and figured out, okay, well, how many students scored in this range? Like take 34.2% of that 3,000 whatever number. Okay, among first-year students at a certain university, scores on the verbal SAT follow the normal curve. The average is around 550 and the standard deviation is around 100. What percentage of these students have scores in the range 400 to 700? Okay. So we can start off here by, here's the normal curve formula. So I inputted this into the calculator. So now what we want to do is, like we've done before, let's get the z-scores of these numbers here. So 400 minus 550 divided by 100. Okay, now 700 minus 550 divided by 100. Okay. So let's integrate the normal curve formula between these two z-scores. And there we go. 86.6% of the students had scores between 400 and 700, assuming this data follows the normal curve. All right. There were about 1,000 students with scores in the range 450 to 650 on this test. About how many of them had scores in the range 500 to 600? Fill in the blank and explain briefly. All right, so to actually give a number here, we need a certain amount of, it's more than just a percent. We're going to have to try and give a specific amount of students. So since they give us this here, this 1,000 students in this range, then what we can do is we can get the z-scores, 450 minus 550 of these two numbers here. Okay, and then 650 minus 550. Okay. Now let's get the percent in this range here. Minus 1 to 1. Okay. So 60, that means that these 1,000 students represent this percentage of the total. So now we can use this to get the total. So we can do the 1,000 divided by, and then this divided by 100. Wait, this. Okay. So that's how many students, the total number of students that took the verbal SAT. So now let's get the z-score from this 500 to 600. 500 minus 550 divided by 100. 600 minus 550 divided by 100. Okay, so now what percentage is this? Okay, now let's take the total number times this divided by 100. 561. Okay. In cycle 3 of the health examination survey, like Haynes, but done in the late 60s, there were 6,672 subjects. The sex of each subject was recorded at 2 different stages of the survey. In 17 cases, there was a discrepancy. The subject was recorded as male at one interview, female at the other. How would you account for this? Okay. So there's this Haynes survey with 6,672 subjects done in this 4-year period, 5-year period. The sex of each subject was recorded at 2 different stages. Maybe they just had 2 different questionnaires, one at year 1, another at year 4, and so they asked the sex. And in 17 cases, there was a discrepancy. Someone said that their sex was male in the beginning, and then 3 years later they said it was female, or vice versa. How would you account for this? Well, I mean, okay, a sex change, perhaps? I don't know. I guess if they're asking from a statistical perspective, how would you account for this? I mean, it's kind of like an outlier. I don't know if you'd call it an outlier, but either a sex change or human error. Probably more human error, I would guess, where they just spaced out and didn't read the question and put the wrong thing. They didn't mean to put that. Okay, we'll finish the rest of these problems in the next video.